Let's take a look at this question. Okay, here is the sun. The sun here, giving out light. Okay. Here is the earth. So that's our earth. Now the earth is moving around the sun. So that's the earth's orbit. Quite a circular orbit. Now in this question, we want to look at a satellite which is about there. It's a man-made satellite, and the name of this satellite is called Soho. I'll say a little bit about Soho after I've gone through this question. Now there is something strange about this satellite. As it's described in this question, it doesn't actually go around the Earth, right? Unlike most other satellites. This satellite goes around the sun. So it goes around the sun just like the Earth. So it follows a very close orbit, to the Earth. It follows a circular orbit around the sun, and this orbit is it has a radius of 0.99 of times of the radius of the Earth. Okay, where I'm taking R to be the no, I don't mean the radius of the Earth. I mean the radius of the Earth's orbit. So R is the radius of the Earth's orbit around the Sun, or the distance from Earth to the Sun. 0.99 R is the radius of Soho's of this satellite's orbit. That means that the orbit of this satellite is 1% smaller. The radius of the satellite's orbit is 1% smaller than the radius of the Earth's orbit. So it goes around in a slightly smaller circle. Okay. Now, and we are given that the period of this satellite's orbit, is one year. But we know that the Earth satellite is 1 year, of course. But we are also told that the satellite's orbit is 1 year. Okay. Now the question is, why is this possible? Okay, why is this possible? So why 1 year? Why possible? Okay, and there are a few options. Now, so this is a rather subtle point. So I'm going to write out the options that are given in the question, and go through them properly. The 4 choices is a multiple choice question. So the first choice goes something like this. I just roughly rephrase it very briefly rephrase it. The first choice, A, says something like the sun's field, sun's gravitational field, is reduced by the Earth's gravitational field. Okay, so that's one option. Now, one choice, the next choice is the force from Earth, or the gravitational force from the Earth is balanced by the Sun. Right, well, when by force we mean the force at the satellite, of course. So let me just make sure that that's clear. At the satellite. Right, at the satellites. There. At the satellite, force from the Earth is balanced. The force on the satellite from Earth, right? The force meaning the gravitational force, of course, is balanced by the Sun's gravitational force. Okay, next choice. The mass of let's see. Mass of the satellite is smaller than the mass of the Earth. Satellite's mass is smaller than mass of Earth. Okay, and last one. Resultant force on the satellite. Resultant force on the satellite is less than the force from the Sun. Right. Now let's look through this. The Sun's field is reduced by the Earth. Now, some of these are quite subtle. At first, when I looked at it, I thought that I can understand this to mean the resultant field at the satellites. Okay, because at the satellite the Sun pulls one way, Earth's gravity pulls the other way. So surely the gravitational field here is reduced. Okay, but if you read it very carefully, you realize that we need to distinguish this statement from the statement D, because D mentions the word resultant, but A doesn't. So after reading through all this and thinking about it for a bit, we would see that we are supposed to understand this statement, okay, as saying that the Sun's gravitational field, that means the gravitational field at this satellite, the gravitational field at this satellite is actually the result of the Sun's field and the Earth's field. Okay, but the Sun's field in this statement, it still refers to the Sun's field, so that hasn't changed. So therefore, it is wrong to say that the Sun's field is reduced by the Earth. It's just that you have the Sun's field here and you have the Earth's field here, and the combined resultant, okay, is less than the Sun's field itself. So that's the proper way to say it. But the Sun's field itself hadn't changed. Okay, it remains one of the two fields acting at this point. Okay, so which means that that's not right. Now the force from Earth is balanced by the Sun. So once again, it depends on how we read this. If you just read this in a very in a not very strict way, in a very relaxed way, force from Earth is balanced by the Sun, we might think that balance here might not mean exactly balance. Okay, it might mean that some of the force from the Earth is cancelled by the force from the Sun, but not exactly. So that's one way to think about it if you're not if you are relaxed about it. But I think that we might have to take this balance to mean exactly balance. Okay, so I think it means exactly balance. So there's a slight we're slightly unsure about this, but let me put a cross there, maybe with a slight question mark. And this one, actually, at first I thought that it is okay, as I said. So maybe I'll put a slight question mark there as well, until we come to an answer that's definitely relevant or correct. Now, C, satellite's mass is less than the Earth's mass. Now, we can't say that that's wrong. Obviously, the satellite is less. The mass of satellite is less than Earth's mass. Earth is huge. Satellite is man-made. Okay, so this is a true statement. But the question is it relevant? Okay, is it relevant? So, does it answer the question? Don't know. Maybe. Okay, maybe. Resultant force is less than the force from the Sun. So, right. There is the Sun's force pulling on it, and then there's the Earth's force pulling in the opposite direction. Okay, so we might think that the Sun would be pulling at it at a certain force, and some of this force will be cancelled by the Earth pulling in the opposite direction. So that seems to be possible as well. That seems to be possible. So again, the question is whether this answers the question. Okay. So there are a few subtle points here. Now, it depends on how we want to do this. Now, if you're actually doing this multiple choice question in the exam, you have a short time. You might have, on average, have just a few minutes to try this, even maybe less, and you want to pick an answer quickly. Now, if that's the case, then after looking through this carefully and thinking through what I've discussed, hopefully, we have to maybe pick between C and D. Now that's without a proper analysis, maybe by thinking about the forces and equations carefully, it's actually quite hard. So at this point, right, if you're in a hurry, I'll explain in more detail in a moment. But let's just say that if we are in a hurry, what might we do? We might look at these two and think, okay, the resultant force is less than the Earth from the Sun. So maybe you could start by thinking about how the resultant force would affect the period. Right? If you look at this question, why is it possible for this to be 1 year? Right? Think about this question. You must start by asking, why not? I mean, what's the problem with having a 1 year period for this this satellite's orbit. Okay. Now the problem with this satellite being 1 year is that it's the same as the period of the Earth, and the problem there is that they have different orbits, the orbits have different radii. And why is that a problem? Okay, that is a problem because for planetary orbits, the period of revolution is directly related to the radius. Okay, that's not something that's obvious. That's something that we would have learned in A-level physics, but if we remember it, but it is not obvious. So let me quickly write down the equation for this. The equation, the equation of forces for a planet or satellite in orbit is given by, if it is a circular orbit, is given by centripetal force mv squared over r is equal to the gravitational force, because gravity is the only force present. Okay, so looking at this equation, now for planetary orbit, it's actually better to use the other form of the of the centripetal force, the other formula, which is m omega squared r. The reason is that omega here is 2 pi over the period. That gives us a direct relation between the period and the radius. So if you look at these two, look at this equation, okay, it is obvious that there's a direct relation between r, the radius of the orbit, and the period. So without actually rearranging and simplifying, we can already see that there's a relation. And so that means that if the radius of the orbit is different, the period must be different. Okay, the period must be different, even without thinking about whether it will be bigger or smaller. We know that it must be different. So that's why it is strange that for a smaller orbit to have the same period. We would expect it to be different. Whether it might be bigger or smaller, all right, we'll find out if we think about it more carefully, but it should be different. So that's one thing. That's why we have a question here. Why is it possible? Now, the other thing is that with this equation we can actually eliminate C, okay, because C gives this reason that satellite's orbit is less than the Earth's orbit. Now, if you look at this equation, you see that the mass of the satellite, if I take m, say m to be the mass of the Earth or the satellite, and big M to be the mass of the Sun. Now you see that the little mass cancels. So the small m can either be Earth or the satellite. You see that it cancels. Okay. So in other words, it doesn't matter. It's just the Sun's mass that matters. It doesn't matter what the mass of the satellite, what the mass of the satellite is, or whether it's the satellite or the Earth. So whether the satellite's mass is smaller than the Earth's mass should make no difference, from what we can guess, all right, from at least by noticing that the mass of the satellite or the Earth cancels. So therefore, we can now say be more sure that this is not the answer. Okay, so once we do that, that leaves us with D as the most likely answer. Now, can we be a little bit more sure? Now, looking back at this, you see that what we have here is say the period down here on this side and the mass. Okay, let me combine the two and write it out more directly. So we have m and omega is this one, so 2 pi over t squared r is equal to gm over r squared, and I'm saying that the mass of the satellite cancels, and that's what we have. Okay. So, and yes, I was saying that the radius of the orbit, if the radius of the orbit is different, the period should be different. Okay, so therefore having 1 year is difficult to understand. But if we look at this equation is for the case where we have only the sun and the satellite, or only the sun and the earth. Right? We don't have these two together, because this formula is just for the force from the sun alone. It's for the force from the sun alone. But in this case, this satellite it is under two forces. It's got a force from the sun. It's got a gravitational attraction from the sun, but it has also got a small attraction from the earth. Okay, so this part here is the GMM over r squared. This part is the gravitational force from the sun. But there is this little part here from the earth. So we have to take this and minus of the earth's force. So this side here, because the earth is there, or is on the other side of the satellite, means that this side of the equation becomes a bit smaller. Okay, so the right hand side of this equation now becomes a bit smaller because we have this additional term here. So this additional force here, and that actually makes it quite a bit more complicated than the original equation, right? Just by having this extra force from the earth. Okay, but luckily we don't have to actually do any calculation. We just have to realize that on the right hand side, the combined value on the right hand side is a little bit smaller than if it is just the sun, right? This is just the sun. So, but because of the Earth's, okay, the force, the overall resultant force on the satellite becomes a bit smaller because the Earth pulls in the other direction. So because it becomes a bit smaller, that's going to affect the period. That's going to affect the period. Okay, and without actually thinking about whether the result is that we'll get a bigger or smaller period, okay, just by this connection alone, we can guess. All right, we can guess that D should be the correct answer, or the most likely answer in any case, compared to the rest. So I've taken many minutes to explain this. All right, and hopefully it's possible to run through all this in our mind in a couple of minutes in the exam. But since we have a bit of time on this video, let me look at this a little bit more closely, to see whether we would expect this period to increase or decrease. Now, without the Earth's force, without this cancelling force from the Earth, if you just look at this, we have an R there as well as an R here, right? What I want to try and see is whether the period of this would increase or decrease. Whether it would increase or decrease. Now, if we look at the original equation, without the Earth's force, so if let me remove this part of it. If I look at it without the Earth's force, let's see what's the connection between the radius and the period. Now it's easier if I move this r over to the other side. So let's do this. 4 pi squared here over t squared. Now if I move this r over, I'll get gm, and I'll get gm over r cubed. I have both of them in the denominator. I'll leave them there for what I'm going to talk about next. But if you just look at this, you see that if r is a bit smaller, like here, like when you go from the Earth to the satellite, the radius of the orbit becomes 1% smaller. So if the radius of the orbit is a little bit smaller, you would expect the period to be a little bit smaller normally. Okay, so that's normally the case when we have just a planet or satellite and the sun with nothing else around. So if I'm just looking at the satellite itself, if Earth is not around, if we have just the satellite with a slightly smaller orbit, we would expect its period of revolution to be a little bit smaller than 1 year. Okay, so Earth is 1 year, a smaller orbit should be slightly less than 1 year. Right, a slightly smaller orbit should have a period that's slightly less than 1 year, according to this relation that we see here. Okay, so when r decreases, t decreases. That's what we would expect normally. But in this special case, where we had the force from the Earth, things are a little bit more complicated, because we had to subtract the force from the Earth. Now, to make things easier, I'm just going to call this F. Let's say I have a force from the Earth F. So that's my F. Force from the Earth. So I need to subtract the force from the Earth. Okay. Now this time, if I add or take away this force on the right, if I now move r over to the other side, divide both sides of this equation by r, I have an additional minus f over r here. Okay. Now without this term, when I did not have this term just now, right, when this was not here just now, you see that if r decreases a bit, the period should decrease a bit. Right? When the orbit decreases a bit, becomes a bit smaller, its period becomes a bit smaller. So if the orbit was 1 year, when you have a slightly smaller orbit, it should be slightly less than 1 year. Okay, that's if that force is not there. But because Earth is here, we have this additional force there. We need to add it. We need to subtract that force. Now, so subtracting this force would have the effect of making the right-hand side of this equation, the effect of making it a little bit smaller. So this means that t must become a little bit bigger in order to make the left-hand side still equal to the right-hand side. So if we summarize what we have said, without this force, without this force from the Earth, making r a bit smaller, like 1% smaller, would make the period a bit smaller. But having this subtracting this small force from the Earth and making the right hand side smaller would have the effect of making t a little bit bigger, so that the left hand side is still equal to the right hand side. So okay, let's summarize. Smaller orbit makes the period smaller, but subtracting this force makes the satellite orbit a bit bigger. So the two effects can end up making the the satellite's orbit the same as the Earth's orbit's period. So that is how it is possible. That is how it is possible for the SOHO orbit to also have a period of 1 year. And this reasoning here also explains why this question was asked in the first place. Because without that force, we would expect the period of the satellite's orbit to be smaller. Okay, so that more or less makes it quite sure that D is the correct answer. Okay, because the resultant force, meaning this one, that's our resultant force, that is mentioned in D, is smaller than the force from the sun, which is just this, which is that's from the sun. Okay, the resultant is smaller because we have to subtract a bit due to the opposite force from the earth. Okay, so finally, let me just say a little bit about SOHO. So this has got nothing to do with the question, working out the question directly, but just an interesting detail. Now, SOHO actually stands for solar and heliosphere observatory. So that's SOHO, SOHO, and it's a satellite which was launched in 1995. Launches 1995 to study the sun. And interesting thing is that it's still in operation today, I think, and it has also, while studying the sun, it has also managed to discover 2,700 comets. So this is the detail which I got from Wiki. Thanks for watching.